Good evening. My name is Moshiwudi Matabata, and tonight I'll be presenting on WRM3701 project. The project is about an analysis of a water supply project to be implemented by the TSHIPISE local municipality. Now, for the introduction, in this project, I was appointed as an engineering technologist to do an analysis of a water supply system that is going to be implemented by the TSHIPISE local municipality. TSHIPISE is a town in Limpopo under the jurisdiction of the Vembe District Municipality. This project is intended to provide water supply to its 5 townships in accordance with the municipality's Water Services Development Plan. The appointment involves designing the hydraulic infrastructure for the water supply scheme, for example, your pumps, pumping mains, bulk supply reservoir, and bulk supply mains. Now, as per requirements, the bulk reservoir should be able to provide 8 hours of supply without pumping. To carry out this design, the EPANET software will be utilized. This software is a computer program that performs extended period simulations of hydraulic and water quality behavior within pressurized pipe networks. A network consists of pipes, pumps, valves, nodes, and reservoirs. Now, this software also tracks the flow of water in each pipe, the pressure at each node, the height of water in each tank, and the concentration of a chemical species throughout the network during a simulation period. Now, the next slide just shows where the TSHIPISE is located. Now, this next slide is the literature review. A water supply system is a system used for the collection, transmission, treatment, storage, and distribution of water from the source, for example, your river, reservoir, and then distributing the water to consumers. Now, a village or a town water supply system is made up of gravity pumping, base transmission, and distribution system from local or distant water source with needed water treatment system. Now, this is just a schematic representation of how the distribution works. It's from the source. From the source, the water goes to the treatment plant, and then from the treatment plant to the storage, and from the storage, the water is then distributed to the tank, from the tank to the village. Now, water supply network. As stated and given in the project brief, the water will be sourced from the Nyangwe River, and the WSDP shows the layout of how the water will be distributed throughout the supply network. The network assumes that each community has a local supply reservoir, which is referred to as the demand centers, as shown below. Now, for the water flow, the scope of work given to me by the TSHIPISE local municipality is to design a network which will supply fresh, clean, potable water to the 5 townships in the region. Now, water will be connected from the river, the Nyangwe River, which is in very close proximity to the above-mentioned townships. The system will begin from the river, where the water will be pumped up the Shikahilo Hill through a pipe into the Shikahilo treatment plant, which is located 700 meters away from the river. The water will be pumped again from the water treatment plant to the highest point on the network, which is the bulk storage reservoir. And from there, only pipes will be installed and the water will be distributed to the 5 townships with the aid of gravity. Now, for a system to function, it has to have components and icons. Now, the components and icons that you find in a network system, number 1 will be your water source. In this case, it's the Nyangwe River. The Nyango River is the source of water and is represented by a reservoir node, which in EPANET is an infinite external source. Now within the network also you'll find the treatment plant. So now water from the available source, water from the river, is treated at the village level. If bulk water is to be used, if bulk water to be used is treated and potable, then further treatment may not be needed at the village level. Now, depending on the source and quality of water in a region, there are several ways to treat water. Now, town level water treatment systems are usually located near headworks. The treatment units are constructed such that flow of water from one unit to another can be aided by gravity, thus in turn eliminating the need for pumping. Now you also find your storage tank within your network. This is required for the continuous supply of the water system whilst pumps are in operation. Now, standby storage provides for continued water supply during unorthodox working hours, like, for example, structural, electrical, mechanical, or treatment process failure. Storage facilities are also needed to meet flow requirements in terms of discharge and pressure. Distribution. In the distribution of water, there are pipes and pumps are required for the system. Now, pipes used in water systems must be approved for potable water use. Approved pipes include polyvinyl chloride pipes and polyethylene pipes. These pipes are normally buried below the frost line to keep them from freezing and to protect them from vandalism. Pumps are required to lift water to overcome the differences in elevation and compensate for energy losses caused by friction and to provide operating head for the end user where necessary. There are normally two types of pumps. Number one, the positive displacement pumps that trap an amount of fluid and then pushes it out. Then the dynamic kinetic pump, which impart pressure and velocity onto the fluid. Now, from the data given on the project brief, I needed to calculate the elevations. Now, the elevation at the Nyangwe River is found at 0 meters. And then the elevation from the river to the water treatment plant was found to be 17 meters, river to the bulk storage 74 meters, etc. Now, for the required bulk storage is given in the project brief as 10,244. Now, the available storage as calculated is greater than the required storage. Therefore, there will be sufficient storage. Now, the following slides are just screenshots from the EPANET. Now, number one needs to set up data, defaults, and units for the system using the Hayes and Williams equation and liters per second. Also set your labels in the default, set dimensions to be in meters as given. Now, these two screenshots are showing the first step. Now, number two, input the needed nodes as per the map given. After inputting all the equations, I then now went on and then inputted the nodes as you can see on this particular screenshot. Thereafter, I went on to set up the time patterns. I was given the multipliers. I just inputted them there and then I took a screenshot. After that, I went to pump curves on the data and then inputted the flow and the head as given on the project brief. Now, after doing all the aforementioned steps, then I went on to insert the pipes and through the network as can see on this particular screenshot. After putting in the pipes and the nodes, then I ran the first single simulation to get feedback from the software. After running the simulation, it was found to be unsuccessful. Then the system, the Ethernet, gives this report to show that the simulation was unsuccessful. Now thereafter, for a successful run, the run that I performed was unsuccessful because of negative pressures experienced. This indicates that the pipe diameters inputted were too small to sufficiently distribute water in the system. So now from the design, the following was observed. A reduction in the diameter of the pipe can compress the flowing fluid. It flows faster, which increases the flow rate. And if the diameter increases, then the flow rate reduces. Now, after the necessary pipe adjustments were made, the run was successful, and now I could process to analyze the system. I analyzed the system and ran the simulation, and the simulation was successful, as you can see on this particular screenshot. Now the next slide is just the results from EPANET, showing the flows, the velocities, then the head loss, friction factors from the EPANET. Now the next slide is just an example of the velocity of pipe 1. I took a screenshot from EPANET showing the velocity for the pipe 1. Now for analysis of the tanks. Now for tank 1, the water treatment plant, depicting head and pressure. The graph below shows the pressure for tank 1 at various times during the 72-hour period simulation. The 72-hour period was given in the brief. Now this graph just shows the head and pressure for tank 1. Now this screenshot, it indicates the pressure, the minimum pressure experienced is 9.5 meters. There no point where the pressure is at 0 meters. It proves that the tank doesn't go empty during the 72 hours period, hence providing a constant storage and constant supply to townships when needed. Now this next screenshot just shows the head at tank 1. Discussions. The impact of pipe diameters on flow rate. In a water distribution system, a reduction in the pipe diameter can compress the flowing water. This will in turn result in an accelerated flow of the water, thus in turn increasing the flow rate. But when an increase in the diameter reduces the flow rate, this means that the relationship between the flow and the flow rate and the diameter is inversely proportional. Now, the impact of the pipe diameter on the water pressure. The static pressure is not affected by the difference in pipe sizes across the system. Instead, when the connection is open, the water pressure moderately decreases, and this decrease is brought about by the large pipes in the system, which allows for minimum flow resistance. The next slide is the analysis of demand centers. Now, all the demand centers are acting as output ends in the design network, meaning that this is where the community have access to the water that is from the Nyangwe River, then treated at the Shikahilo treatment plant to make sure that the water is suitable for human consumption and domestic use. Water pressure needs to be adequate enough to be able to achieve the recommended flow and velocity for each household tap. Now, this is just a screenshot from demand center number 1, depicting the demand, the head, and the pressure. Now, after all the steps that I undertook, this is now the system layout indicating the velocity of all the pipes within the network. The next slide, the system shows the pressures at each node. It is clearly seen and depicted in this particular screenshot that there's no negative pressure in the system. This signifies that the system will work as efficiently as needed to distribute the water to the townships. Now the next slide is the final system layout. After all the adjustments and all the labelings, this is now the final system layout. Now in conclusion, when designing a bulk water network, reliability, functionality of the component is important. Thus, TSHIPISE local municipality requires a system that will be reliable for its residents. A fully functional design is able to provide water at all times with little to no disturbances in the distribution network. From this report, it is very evident that the interrelationship between the reservoir size, pipe diameter size, storage tank size, supply and daily demands affects the type and how the efficient the system is. This report demonstrates the crucial importance for all the network components on the system reliability. The function of a pump station in the overall distribution system operation can also affect the determination of capabilities. Now, to eradicate all the possibilities of experiencing negative pressures in the system, 2 pumps were installed for all uphill pipeline sections. For example, between the Nyangwe River, the abstraction point, to Shikahilo Water Treatment Plant and Shikahilo Water Treatment Plant to the bulk storage reservoir. Now, this is done to provide enough head to push water uphill and increase the flow in the network. Pumps, piping, and equipment must be protected from the weather and high temperatures to avoid rapid damages. To keep the network working efficiently, it is important for the TSHIPISE local municipality to prioritize the maintenance of all components in the network. Now, it was said that water is life, so it is the responsibility of the municipality to ensure that the citizens have got potable water at all costs. Thank you so much.